Hello everyone, welcome to mentorbuddy.com. This is your mentor Gurvansh, and today we are going to see a project on heart disease classification. So guys, as we did in our previous sessions using our different algorithms, this particular project is for the classification problem statement. Hence we are going to use one of our classification algorithm which we used. So in this particular project I am going to show you how do we actually perform a project given to us according to the problem statement using the KNN algorithm. As usual, our first step is to import the libraries. So first of all, I'm going to import the basic libraries such as NumPy, SNP, import pandas as PD, import matplotlib dot pyplot as PLT. Other than this, we are going to write import cborn as SNS. So these are the basic libraries which we are going to use in our particular project. Other than this, we are going to use the scikit-learn library, and as we have done in the previous sessions, we are going to use the scikit-learn library the same way. Wherever we need it, where we will import that module at that time only. Okay, so let me first show you how do we import the dataset. So we write df is equal to pd dot read underscore csv. Then we write the file name. Now the file name available for us is the heart.csv file name, which is this particular file having around 303 rows and multiple columns. So first I will import it and then show you the dataset again. So I'm going to write over here heart.csv. Let's print this. Print data frame. So when you print this, you get 303 rows with 14 columns. Now guys, in these 14 columns we have age, sex, CP, TREST, BPS, cholesterol, FBS, REST, ECG, THALAC, XANG, odal peak, slope. So these are different parameters or features required in order to know the features of a heart disease. Now guys, this is a classification problem statement, and the last column as usual is the output column, the one which we are going to predict. So we have the target column with the two classification, ones and zeros. One means that yes, you have a heart disease, and zero means that you do not have a heart disease. Now guys, here few of the columns are truly numerical, while few of the columns are categorical values. For example, we have the sex column. The sex column over here has values ones and zeros, representing ones as male and zeros as female. In the same way, we have this REST ECG, whether you have some value in REST ECG or not. Then we have XN, which is 0 or 1. Then we have FBS, which is 0 or 1. So these are the few categorical columns which we have in our data set, but still needed for our output. Okay, as you all know, the next step which we do is to get the information on our particular data set. So we write df.info and we are going to print this info. So we write print df.info. Let's run it. Now guys, it says that out of 14 columns, all of them are integer type numeric columns, but as I've already explained you, the columns over here are categorical also, but are taken as a numeric value with encoding itself. So we do not need other special encoding. It is already done over here. Okay. Moving on. Now guys, here we can perform some of the tools or some of the plotting tools we can use over here. One of the plotting tools which we can use here is a very simple histogram plot. So we can write like this: df dot histogram hist without first, let's say, without giving any values. Then we are going to write plt dot show to get the output on the screen. So when we run this particular histogram, so this is the histograms we are getting of different columns. Now if you look over here, the histograms are very small, barely readable. Let's try to increase the figure size. So for this we need the figure size parameter. We write figure size is equal to and we give x and y values. How much do you want? So let's get started. I'll first write 8 comma 8, so both of the sides it will be 8 by 8. Now this is looking a bit better. Now let's try to increase the size bit more. Okay, so here I'm going to write 14 comma 14. You can give any values also. Here I am trying to make a square. You can make rectangles also. So if you look over here, now our histograms are looking much better. So it says that it is giving us histograms of individual columns. Okay, so first histogram is of age column, the range it is showing. Then there is the sex column. It is saying that you have only two values in the sex column, zeros and ones. Then we have CP. It says that CP consists of four values and these are the count of those four values. Then we have TREST BPS, then we have cholesterol, then FBS, rest EC. Now guys, the range columns, the range plot you are seeing, means the area plots you are seeing are the numeric columns. So numeric columns are forming the areas. The column plots which you are seeing right now, columns which you are seeing are the categorical column, showing that these columns only have like discrete values or categorical values. For example, target zeros and one, right? It is the output column. In the same way we have CA. CA only has four values, means 0, 1, 2, 3, 4, 5 values, and these are the count of those particular values. So this is how we get a histogram in our particular plot. Next thing is that we can simply get a very easy pair plot to, let's say, as we have discussed earlier also, while we have the dimensions more than 3, it is not possible to plot all of the values, right? So in order to make it possible to plot all the values, what we do, we use Seaborn library to get the pair plots, right? So here we can write simply, we can write SNS dot pair plot, and pair plot of what? Pair plot of DF data frame. Then I'm going to write PLT dot show to show that particular pair plot. Now when you look at this particular pair plot, okay, it will take some time. The reason is that it is trying to make different combinations of 14 columns. So different combination of 14 columns can take huge amount of time. So it is making different combination. Let's say one few combinations can be all the input column versus the output column. So we will get around 13 columns for that. First age column with the output column, sex column with the output column, CP column with the output column, right? So those are the most basic plots, pair plots we can make. So age with target, sex with target, CP with target, TREST BPS with target, cholesterol with target, FBS with target, right? So you can get normally 13 plots you can get with the same combination. Now we can make different plots also, like age sex plot, age CP plot, age tax plot, making the combination very high. Now as you guys can see over here, this is what I was trying to say, that when we make column plots of too many values, this is the reason why we generally do not prefer pair plots also when the number of columns is way too high. Now here you can count, okay? So we write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In the same way we will have 14 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it has made 14 comma 14 combinations of pair plot, and barely any one of them is visible, right? Barely any one of them is understandable. All of them are visible, but barely any one of them is actually visible. Now what we can do over here is we can reduce the number of columns. How we can do this? So as you guys can see here, we got the individual plots, right? Here when you see, we have few numeric columns. So what we can do is that to get the more appropriate values, we can create the pair plot just for numeric columns. Okay, so for that what I'm going to do, for that I am going to first extract those values. We are going to extract those columns from our data frame and then create a pair plot for that only. So here what I can do, I can just simply write create a variable with the name numeric columns, columns columns, equal to, here I can prepare a simple list of the column names from our data frame. So one of them is the TREST BPS. So what I will do is that I will just quickly copy and paste the name so that I do not get the spelling wrongs, and you should also do the same thing, because if by chance if we get the spelling wrong, there is a possibility that it will create an error. So here we can go like this: age test BPS. So I'm going to write over here age comma test BPS. Let me just quickly paste it, comma we have cholesterol, CHOL, cholesterol was CHOL. Then we have thalec, so I will copy the thalec value. So we have thalec, then we have old peak, right? So I'm going to copy this, go back down, thalec, then we have old peak. Now keep, as I have already told you, please do keep in mind that the spellings are correct, otherwise you are going to get the error. So here I'm just going to paste old peak. Now these are the numeric columns which we have. Now what we can do is that we can simply create a very normal, very easy pair plot of these numeric columns. So I can write like this again, see SNS dot pair plot. Again take from the data frame, and this time take the numeric columns. Okay, take the numeric columns, then we can just write SNS plt dot show to show the plot. Let's see what is the output this time. Now what exactly should happen this time? The pair plot should only take the numeric columns and get the output according to that. So here, as you guys can see, the plots have been reduced very much. So we will have a combination 1 2 3 4 5 5 by 5 25 plots are here. 1 2 3 4 5 1 2 3 4 5. Yes, so the first row is showing you the combination of age with the rest of the column. So age with age, age with test BPS, age with cholesterol, age with thalec, age with old peak. The same goes for test BPS, the same goes for cholesterol and thalec and old peak. Now if you look at the left diagonal, the left diagonal is looking somewhat same to the histogram plot we got, right? So the left diagonal is showing the combination of age versus age, test BPS versus test BPS, and so on. Now guys, with these pair plots of numeric columns, we can get the heat map using the SNS library itself. Now this heat map helps us to get the correlation factor, which will help to know which column is actually more profound, or which column is actually how the columns are related to each other. So we can write SNS.heatmap, and this heat map works for the numeric column, so keep that in mind. We can create the correlation between numeric values itself. So we have df, again I'm using the numeric columns. Then what kind of heat map we are creating? We are creating a heat map depending upon the correlationship of our numeric columns, right? Now when you do this, your heat map should be generated. So let me first show you what kind of heat map we are having. plt.show. After this, if some changes are required, we will make those changes, right? So if you look over here, this is the heat map we are getting, right? So it is just showing us the color, and the colors are not that identical. Now what we can do is that this heat map is not showing us any value, right? To get the values, to get the actual numeric values, actual numeric answers, what we can do is that we can put a parameter over here, which is annotation, okay, annotation, and we say that yes, we need the annotation, so the annotation should be true. Let's try and see the output now. Now see, we get the annotation over here. As usual, the left diagonal is 1 1 1. Other than that, it is showing us the correlation between different columns, different numeric columns, right? Here still you guys can see the values are looking good, but coloring. Now if you want to change the color of this particular plot, we have the parameter which is known as CMap. Okay, so CMap have different coloring options. CMap, one of them I remember, and that is the terrain. You can change the CMap. Now this is the coloring map, okay, color map you want to use for the whole thing. So with this, see, now the color looks pretty good. So this is the another coloring you can choose for your heat map. Let's see now what I'm doing is I am purposely creating an error. Now the spelling was terrain, but I am purposely creating an error. The reason is that, see, you will get a value error like this. Terrain is not a valid value for name. With this, it will show you all the names you can use to create a C map of your values. Now if you look over here carefully, this is the reason I purposely made an error over here, made a typo over here, so that I get all the values. Now you can experiment from these values and try to understand what are the different colorings we have. So let's try one, or let's try a few more. Okay, so this time let me put prism over here. PRISM, prism. Let's see what is the output. See, now prism color is different now, but I do not actually like it. Let's put terrain itself. So terrain looks like this. Now guys, these are few plottings we can use to understand our data sets. We can get a histogram to understand what are the value ranges we are getting, or differentiate between the different values. We can use the info to get the direct written info of our columns. Now with the written info, you can clearly see that all of the columns are non-null. Right now, when all of this process, as you know, is known as EDA. Now while doing this EDA, we try to understand our data, and in order to get to know which data pre-processing steps we have to apply. Now all the values are integer, so no encoding is needed. All the values are present, there is no null value, meaning missing values is step will also be removed. Then let's see. Yes, first of all, obviously we have to extract our x and y from the dataset. That is different. Okay, now let's look at the difference of the values. See the scaling. Let's look at the scaling. So scaling is pretty different now. 2 digit, 1 digit, 3 digit and float value. In order for this scaling to work much better, we are going to perform standard scaling. So here I will start with my data pre-processing steps. First of all, I'm going to extract my x and y from the dataset. So I will write the x is equal to df.ilog, extract all the rows, comma, as for the columns, extract till -1 dot values. Then I'm going to write y is equal to df.ilog, extract all the rows, comma, all the, as for the columns, just get the last column dot values. With this, my x and y will be extracted. Now as previously determined, we are just going to use the standard scaling pre-processing step. So I'm going to write from sklearn dot pre-processing import standard scaler class. So here I'm going to write sc is equal to standard scaler. Then we write x is equal to sc dot fit underscore transform. Then we write x. With this, our x will be converted into same scale, right? Our y is already have x and y values. Now as you all know, since this problem statement is of classification and our dataset have x and y, we have to split it into training and test set. So we write from sklearn dot model selection import train test split. Then we write xtrain xtr comma xtest comma ytrain comma ytr ytest is equal to train test split. We give x comma y comma test size is equal to 0.2. so I am giving the ratio of 80 to 20. Then comma random state is equal to 0. So once I do this, my training x and y will be divided into training size and test size. After all of this is done, what we do, we import our algorithm, train it and try to get the prediction for it, right? So we can simply write from sklearn dot neighbors. Now the algorithm which we are using is the KNN algorithm and it is a part of neighbors module. Import kneighbors classifier, right? So here we write the name of the object is classifier. So you can create any name. I'm giving the name it as classifier. Classifier is equal to K-neighbors classifier, and here, as previously explained in the KNN class, we need to give the number of neighbors. Okay, so the number of neighbors I am giving over here is 8. You can give any number. With experimentation you will understand which neighbor value is working the best. Here with the experimentation we know that the neighbors 8 value is working the best. Now what I'm going to do is I'm going to write classifier dot fit. We are going to fit the values xtrain comma y train. Here our model will be trained. After the model is trained, as you all know, we are going to get the predictions. When we do the prediction, we also perform the testing phase and we get the accuracy. So we write from sklearn dot metrics import accuracy score and confusion matrix. So here we are trying to create the accuracy score and confusion matrix. After this we can write y predict is equal to classifier dot predict the value using xtest, right? And then we can get our accuracy score, which I am storing in ACC. So I'm going to write accuracy score between my y test, yte and y pred. Then we have confusion matrix is equal to create a confusion matrix between y test comma y pred. Now I am going to print the accuracy score only, and with this I am going to plot the confusion matrix. To plot the confusion matrix we need the MLXtend library. So here I am going to write from MLXtend dot plotting import plot confusion matrix. After we get this, we can simply write plot confusion matrix using CM, and then we can write plt dot show. When we run this, we get this particular output. It says that the accuracy score, the accuracy which I am getting is 88% out of the trained model. Our algorithm is able to predict the output with the accuracy of 88%, and this is the confusion matrix we are getting. On the left hand side we have the true label, on the bottom side we have the predicted label, showing us that the left diagonal says that we have the correct values, the right diagonal says we have the wrong values. Here if you try to read this confusion matrix, it says that out of 27 zero values, 24 were predicted correct as 0 and 3 were predicted as 1, which is not correct. Then it says out of 34 1 values, 4 were predicted 0, which is wrong, and 30 were predicted 1, which is correct. So left diagonal shows us the correct values or correct predictions, whereas right diagonal shows us the wrong predictions. So this is how you get the confusion matrix. Now here also in the plot confusion matrix you can use the CMap to change the coloring. So we have CMap, and let's try to use the same terrain and see what we are getting. So this is the product of terrain over here. Again you can try different combinations. So let's try prism over here and see the coloring. Now this is the coloring for prism. I actually do not prefer this. For this I prefer blues. So blues is for blue color. Okay, wrong name, no problem. Let's check. Okay, B is capital, CMap is blues, B is capital. Okay, let's keep the blue, B capital, blues. Let's run it. So this is the normal first plot which we get. Now guys, this is how we actually perform a complete model, starting from the importing of libraries, then importing the data frame, getting to know our data set using different plotting, different techniques which we already shown, getting the heat map. Now if you go through the heat map of the correlation, as usual, left diagonal is showing you the correlation between the column itself. So first is age, or obviously it's going to be 1, then and so on. So it says that the correlation of age and test BPS is positive, but it's just slightly over 0, so it is not that strong correlation but still positive, right? So if you say combination between cholesterol and phthalac, it is very close to 0. So it says that both of them have no correlation to each other. Now if we go through this particular correlation matrix or correlation heat map, the best or the most relatable columns we have over here is phthalac and old peak with a minus 0.34 correlation. They are having a negative correlation. If phthalac rises, old peak will reduce. If old peak rises, phthalac will reduce. So this was the heat map of our columns. Now guys, whenever you create any kind of model, we should try a extra testing phase in which we should give our own values. Now whenever you try to give your own values, they should follow the same combination, same nmap configuration your x is following. So for our x, if I simply print x, let's say print x now. So if you look over here, x will have 13 values, right? But it is coming this way. Now I will try to make the same configuration. Okay, so I'm going to write x test is equal to np dot array. We are trying to create a numpy array with the combination of double brackets. Now if you see here, so what was I trying to say is that you have to follow the same logic. See, we have outer brackets at the starting and at the end, then we have inner brackets containing 13 values. What are these 13 values? 13 values are age, sex, CP, test BPS, cholesterol, FBS, and so on. So we are trying to give the same values. So here, what is our first value? Age. Let's say we give 63, so 63 is the value. Second was our age, so sorry, sex. So for sex, let's say we are talking about a female, 0. Let's say okay, so CP, let me give you the value. CP should be 2. Okay, then test BPS I will give 120. So CP is 2, test BPS is 120. So I'm giving my own values. Okay, but in the range, well in the range, the same range our columns were actually having. So we have cholesterol, FBS, and rest ECG. So cholesterol, let's say, is 230, and then we have 0, 0 I am giving. So our ECG is done. We have phthalac, xang, old peak. So phthalac is a numeric value. For phthalac, let me give 140, comma xang, old peak. Okay, xang, let me give 1, comma old peak, let's give 2.9, comma then we have only 3 columns: slope, CA, and thel. So for slope 1, CA will be 0 and thel will be 1. So here I have tried to create the same combination of our x test. Then, as you know, we have to perform the same pre-processing step. What is the same pre-processing step which we need? Which is to perform standardization. So I'm going to write x underscore test std. For standardization, I'm going to write sc dot fit and transform, or we'll just have to write sc dot transform, because our data already know, our object already know what to do. So x test, then we are going to predict. So I'm going to write x test predict is equal to sc classifier dot predict. Now we are using the classifier dot predict using our x test std. Then we can print our x test predict. Let's run it. So it says 1. So 1 is the output. It is saying that yes, you have a heart disease. Now you might be thinking, sir, we just gave random values, how do we know that it is correct or not, right? So for this we can try a different logic. What you can do, you can at random, you can take any value from this any row, any single row value. Let's say you are selecting this row, so you just copy all the values, meaning 45. So instead of 63 you will get 45. So age will be 45, sex will be 1, CP will be 3, test BPS will be 110, cholesterol will be 264, FBS will be 0, meaning all the same values you give, and then at the 299 the value of the target should be 0. You should not have a heart disease. So you can replicate the same values at random from all the values, at random a single row, select a single row, give the same values over here and try to see whether it is getting the correct answer or not. Now keep this in mind, your accuracy is 88%. So out of 100 run you do, 88 should be correct and 12 should be wrong. So keep that 12 number in your mind before doing this experimentation so that you do not get disheartened too much. Okay, so this is how you perform any kind of project. With this you can obviously add many more steps whichever you want. You can add other plots like bar plots or column plots, whatever logic is coming in your mind you can try it and try to represent that particular thing on your project whatever you are doing. So guys, with this I would like to end this session here. I hope that you understand how to perform a project of machine learning, of data science using machine learning logics and Python programming language. So guys, bye bye, take care, and thank you for joining us on mentorbuddy.com.